Hi guys, we are looking at the fundamental theorem of algebra today. So, first thing we're going to take a look at is Descartes' rule of signs. It allows us to determine how many positive and negative zeros exist. So the test says to look for sign changes of f of x and f of the opposite of x. So what that means is we are looking for how things change. So let me give you an example here. With f of x is equal to 3x to the third minus 7x squared minus 4x plus 5. So we want to look at how many times the sign changes in this. So I start off in the positive. 3x to the third is positive. 7x squared, there's a minus in front of that. 4x, there's a minus in front of that. And 5 is back to being positive. So I changed from positive to negative. It stayed negative, and I changed back from negative to positive. So it changed twice. There are two sign changes here. So that means there are either 2 or 0 positive zeros. And the reason I say 2 or 0 is because it will go down by 2. They go down in pairs. So if there are 2 sign changes, then we could have 2 zeros or no zeros in there. If you started with 7 sign changes, you could have 7 or 5 or 3 or 1 of those zeros. The other thing we look at is f of the opposite of x of that same function. So if I have f of the opposite of x, then I'm going to put a negative x in for all of these. So negative x to the third is going to make that negative out front. And then if I put a negative x in for x squared, that negative times negative is going to be a positive. So that's going to stay a minus x squared. Then if I put a negative in for x on 4x, that makes that a positive 4x, and that makes that a positive 5. So then I look, and I started off with a negative, I stayed negative, I got a positive, and a positive. So the only thing that happened was the negative to a positive. So then we have one sign change. So that means we have one negative 0 because we're dealing with f of negative x, or the opposite of x. And the reason we look at this is because it helps cut down on possibilities. Of our zeros. The other thing we look at is the multiplicity. And so when we're dealing with multiplicity, if I give you a graph of f of x is equal to x, let's say, plus 2 quantity squared. Well, what does that really mean? We have x plus 2 and we have x plus 2. So that means my zeros on this graph would be at negative 2, 0. And then over here would also be negative 2, 0. So it's only there one time. So the 0 is negative 2 with a multiplicity of 2. Has a multiplicity of 2. It occurs twice. So when we have an even multiplicity, it is going to bump, bounce, or touch, depending on what you want to say. It's a bump, a bounce, or touch on the graph. If you picture that graph, x plus 2 quantity squared, then it's right over here at -2. It's going like this. It comes down and flies right back up. So it bumps, bounces, or touches the x-axis. And then it goes back the way it came from. However, if you have an odd multiplicity, it's going to do the opposite of that. With an odd multiplicity, so this could be a multiplicity of 1. When it occurs one time, it is going to cut or cross the x-axis. So let's say we have f of x is equal to x plus 1, x plus 3, and x minus 4. Well, if I sketch that over here, my zeros are -1, -3, and a positive 4. So I'm at -1, -3, and positive 4. So -1, -3, and positive 4. And I know based on my end behavior, since if I multiplied all this together, I'd have a cubic. So it would be coming from -infinity. It's going to go up, it's going to cross the graph, it's going to cross back down, and it's going to come back up and head towards positive infinity at the other end. We still don't know where those y values are just yet when it's crossing over, but we know that it will look like that. So we're starting to tie some things in together. So find all the zeros of x to the third plus x squared minus x minus 1. So we could use what we learned in our previous lesson, finding those zeros. We could try to factor by grouping. We could do some synthetic division. I'm going to go with factoring by grouping for this one. So if I factor by grouping, I group the first two, then I have x squared, and then I have x plus 1 left over. Then I group the second two, I have -1, and I have x plus 1 left over. And I set that equal to 0. So I have x squared minus 1, and x plus 1. And then x squared minus 1 is one of my special cases. That's x plus 1, x minus 1, and then I still have x plus 1. Okay, so then we have 3 zeros there. We know that x could equal -1, x could equal -1 again, I'm jumping to the end, or it could equal a positive 1. So then we have -1 with a multiplicity of 2, which means at that point on the graph, it's going to bounce. We have a cubic function, so I'm thinking John Travolta like this. So if I sketch this out, I don't know my y-axis, so I'm not going to sketch anything on my y-axis. But I do know on my x-axis, I'm looking at -1 and I'm looking at positive 1. So -1 is a 0, and positive 1 is a 0. So now, I'm starting at negative infinity, and I go up. As I hit negative 1, it's a multiplicity of 2, so it's not going to go up through it, it's going to come back down. And then I'm going to go up to 1, and since it's a multiplicity of 1, it's going to keep going up. And notice, we've satisfied the shape of the graph and those zeros. So we're taking care of each piece and starting to put together this graph. Alright, looking at this one, x squared minus 14x plus 49. That one looks factorable to me. So I need two numbers that multiply to 49 that add to negative 14. That looks like probably negative 7 and negative 7. So x minus 7 and x minus 7 is equal to 0. So that means I get x equals 7. That's a multiplicity of 2. So now this is an x squared graph. I'm over here at positive 7. And I put a dot. I know since it's x squared, it's going to be that parabola shape. So I'm starting up at the top. It heads down. It bumps, and it comes back up. Alright, x to the 4th plus 3x to the 3rd minus 8x squared minus 22x minus 24. So, let's find some possibilities for rational zeros. My p-value is negative 24. My leading coefficient is 1, which is nice because that means we'll divide by 1, but that still means we have 1, 2, 3, 4, 6, 8, 12, and 24, and all of the positives and negatives of those. That's a lot of options. I would go ahead and plug that in your graphing calculator and find one that looks like it goes. So if I plug in my graphing calculator, I get a negative 4 is what I see as my first one that popped out. And then I'm going to put synthetic division up here to do. So I'm going to bring down that 1. So I have, oh, that's a 1. So I have 1 times negative 4 is negative 4. 3 plus negative 4 is negative 1. Negative 4 times negative 1 is 4. Negative 8 plus 4 is negative 4. Negative 4 times negative 4 is positive 16. Negative 22 plus 16 is negative 6. Times negative 4 is positive 24. It is a 0. You could then say, okay, now I need new zeros for 6. So 1, 2, 3, 6. I was able to also see 3 on my graph from my original graph, or you could go ahead and graph a new one. I'm going to keep dividing this out here since it's still in cubic and it doesn't look like it would factor out for us. So bring down 1. 3 times 1 is 3. Negative 1 plus 3 is 2. 3 times 2 is 6. Negative 4 plus 6 is 2. 3 times 2 is positive 6. We get a 0. Okay. From that point, we have x squared plus 2x plus 2. I didn't see it cross the graph anywhere else. So, let's find out. I need something that multiplies to 2 and adds to 2. I can't think of anything that would do that. I'm going to go quadratic formula here. So x equals opposite of b plus or minus b squared minus 4 times 1 times 2 all over 2 times 1. So I get negative 2 plus or minus, so I get 4 minus 8, square root of negative 4 over 2, we know the square root of negative 4 is 2i over 2. So negative 2 over 2 is negative 1. 2i over 2 is just I. So negative 1 plus or minus I. So our zeros then are, if I go back up here, negative 4 and 3. And then we have 1 plus I and 1 minus I. Now we're not going to graph 1 plus I or 1 minus I. Those don't show up. But we are going to be able to use our information to graph the rest of it. So it was an x to the 4th, which means even we're thinking going like this. It wasn't flipped over. So my two real zeros are at negative 4 and positive 3. And neither one has a multiplicity of an even number, so it just looks like this. So there's all the real zeros. There's my graph and what it looks like. And we are done there. All right, find all the zeros of this. Well, the first thing you need to do, well, you can do this a couple different ways. I would move the 19 over and set it equal to 0. But we are just going to plug this in our graphing calculator. So you could move the 19 over, set it equal to 0. And then you're going to do second calc 0. And remember, you have to tell your calculator which 0 you're looking for. So tell it just to the left of that 0, just to the right of that 0, and kind of hone in on that spot where you're wanting it to look. Or you could put what's on the left in y1, you could put 19 in y2, and you could find where it intersects with 19 if you wanted. I'm going to use the second calc 0 on mine. So I would pause this now and try it. I'm going to give you these 0 answers. So x equals 1.74, or is approximately equal to. It's approximately equal to negative 2.40. And it's approximately equal to negative 3.35. So not always will these be nice, rational numbers that you can find. They may give you those kind of ugly decimal numbers that you have to, you just have to use your graphing calculator. Okay, properties of roots and polynomial equations. So if a polynomial equation is of degree n, the equation has n roots. So that's something we haven't talked about, but you may have noticed the pattern that if we have a degree of 3, we have 3 zeros or 3 roots. If we have a degree of 7, we have 7 zeros. That last example we did before the graphing calculator, we had 4 zeros. And then it was a 4-degree term. So then complex zeros occur in conjugate pairs. So if a plus bi is a 0, then a minus bi also is a 0. So they'll always be in pairs. You'll never have a complex just on its own. So this says find a 4th degree polynomial with real coefficients that has negative 2, 1, and 2i as zeros. We just said that those complex values have to come in pairs. So this is really like 0 plus 2i. So then we also need 0 minus 2i, or just negative 2i. And then we have positive 2i. Those are our two complex zeros. So what I'm going to do is write out f of x is equal to x plus 2. That's my negative 2, 0. X minus 1. That's my 1. And then I have x minus 2i. And I have x plus 2i. but it says with real coefficients. So I can't have that plus 2i minus 2i there. These two out front are okay, so they can stay as x plus 2, x minus 1. I think your book, when you're checking your answers, is going to multiply everything together, so if you are checking, you may need to do that. The only one that I have to multiply is this. So I get x times x is x squared, and then I get plus 2ix, and I get minus 2ix. And then I get minus 4i squared. So what I notice right away is these 2ix's cancel since they're opposites. So I still have x plus 2 and x minus 1. And then I have x squared and that minus 4i squared. Well, we know that I squared really is negative 1. So I have minus 4 times negative 1, or just plus 4. So there's my 4th degree polynomial with those zeros. Okay, so find a polynomial of degree n that has the given zero. So the zero is negative 3 and it has a degree of 2. Well, that would be x plus 3. But if it needs a degree of 2, we need another value there. And we can't come up with another 0, so we could just give it a multiplicity of 2. X plus 3 times x plus 3. It still has a 0 of negative 3, but has a degree of 2. Okay, so then this next one has a degree of 4. We have 3 zeros. So we're going to have to pick one of those to give a multiplicity of 2. So this is one where there isn't a right or wrong answer. So we have x minus 0, or just x, and then we have x plus 1, and we have x minus 2. So I need a degree of 4 though, so I'll just say x squared. You could have made any of those be a squared. Alright, this one is a degree of 2. I have negative 6 plus I, but if I have negative 6 plus I, then I also need negative 6 minus I. So if I use negative 6 minus I, then this is what it looks like. I need to do x minus a negative 6 plus I, and x minus a negative 6 minus I. So now if I simplify that, x minus a negative 6, I get x plus 6 minus I, and I get x plus 6 plus I. We still can't leave it like that. So now I'm going to have to multiply all of that in. So x times x is x squared, and then x times 6 is 6x, and x times plus I is ix. Then I have 6 times x is 6x, 6 times 6 is 36, and then I have 6 times positive I is 6i. Then I have negative I times x, so minus ix. I have negative I times 6, so I have minus 6i. And then I have negative I times positive I, which is minus I squared. And notice I wrote that so that I could combine these pieces pretty easily. So I have x squared here. And then I have 12x, positive 6x, positive 6x. And then this ix, negative ix cancels. Then I have plus 36. And I have 6i, negative 6i, those cancel. And then I have minus I squared. So I squared is negative 1, so I have minus a negative 1, or plus 1. So in this case, I have f of x is equal to x squared plus 12x plus 37. Alright guys, I know that was a long lesson. We covered a lot of stuff there. If you have questions, please come in and see me. I will see you in class.